Okay, so first of all, thanks for coming to this talk. We're going to talk about transactions and concurrency control. The things about myself. Yes, my name is Vlad Mihalcea. I'm coming from Transylvania. Check out the logo, probably the coolest one there. Yeah, I work for the Hibernate project, and I'm a Java champion. I do a lot of writing, also on my blog, and I wrote this book, which this presentation is pretty much based on. So now let's start with really important things. You know, when it comes to security, you already know that if you don't have security, or if the lack of security can lead to very serious issues. However, even lack of concurrency control or improper use of transactions can lead to problem like this one. Flexcoin used to be an e-wallet Bitcoin, an e-wallet for Bitcoins, and in 2014 it shut down because of an issue which resulted in a loss of all Bitcoins. At that time it used to be around $600,000, and let's see why. They written on their page that the theft was enabled by a flaw in their application, and there was a hacker who used multiple simultaneous requests, and the attacker realized that he can actually withdraw more than the money that was in the account. And that, actually they could not recover from this, so eventually it had to shut down. And it's not the only one, because this is the next day, another exchange for Bitcoins also got hacked, and they lost 12% of their Bitcoins. And they even, but they didn't have to shut down. So this one is still running today. So let's see. They provided more info about what happened. So it's exactly the same scenario. The attacker used multiple simultaneous transactions from multiple accounts, and they withdraw more than they were allowed to, and that resulted in a negative balance in the first account and more money than were allowed to transfer. So let's see how difficult it is to emulate this. So we have a very simple method, a transfer from an account to an account, and we have a sum of money which we can transfer. So what do we do there? The first thing we're reading the balance. If the balance allows us to transfer that amount of money, we withdraw from the from account, and then we add to the two accounts. It's pretty simple. So now the get balance is just a very simple implementation where you just check the balance in that particular account. And then when you add the balance, you just have a single update statement that does that. It's pretty straightforward. And you even write a test for it, because that's what we're supposed to do. So you write this test where you have $10 in one account and 0, and then you transfer 5. So of course you have to have 5 and 5. And then you transfer another 5, and of course you have 0 and 10. So it works properly. And if you try to withdraw more, it will not work. So you have confidence that your transfer method works as it's supposed to. So everything works just fine, so you ship it into production. However, that was only for serial execution. You didn't test it with concurrency in mind. So for that, we are slightly changing the unit test. So now we have two countdown latches. The first one is to allow us to start all the worker threads at the same time. The second one, the end latch, is for the main thread to wait on all the worker threads to process. So here's what we're going to do. We just create a number of worker threads for the wait on the start latch to start on the same time. We do the transfer, and at the end, we're just going to check the balance. What's the balance in those two accounts? Because at first, we have the same initial state that we had for serial execution. So guess how much money are you going to have in Bob's account if we run this one? And let's see. It's based on the number of threads. The more threads we create, the more money we can deduct. So yeah, that really works. I have it on my GitHub repository, so you can test it more. You can test it on any isolation level. It's broken by design, actually. So what is the problem with this? Is the database? I was using PostgreSQL, so you can blame the database, because we know that databases are ACID, and the database should have protected us against issues like this. However, it's not a database here. You know, if you check again, you do the read, and then you do the check. It's a read-write-modify pattern, but that happened in one transaction, and then the write happens in a different transaction. So this is a very big problem, because if you do the reads and the writes in separate transactions, the database cannot really help you. So you still have to do and apply this ACID and take ACID into consideration based on how it was designed to work in the very first place. So actually the concept was, the way we wrote it was broken, because the get balance and the add balance were executing in different transactions. However, you might think that this is just an example that probably in reality nobody would write that code, but it's not the case. There's one paper from Peter Bellis, Acid Rain is called, and he analyzed 12 open source e-commerce applications, and out of all 12, only one did not have any vulnerability. The rest, 11, had 1, 2, or 3 vulnerabilities based on the shopping cart or whatever operation that were tested there. So it's not so uncommon. So now let's see what we can do about it, because you know the whole theory behind database transactions is actually very, very old. This paper is actually older than me. It's from 1981, and right from the start, Jim Gray. Do you know who Jim Gray was? Does anyone know who Jim? Yeah, Jim Gray was the person who actually he did all the initial work based on how data should be protected by data in a database systems. He actually initiated all this work related to transactions. So very much a lot of things we had now we owe to him. So in this paper he describes right from the very beginning these 3 properties. So at first there was no I, there's only A, D, and C. So let's see what those mean, because those are just acronyms. Atomicity is the simplest one to understand. You just have multiple statements which should all be embedded in a single unit of work, which either works or when it fails, you roll back everything. That's the easiest one to understand. Consistency is very tricky, because in different contexts, it means different things. In the context of ACID, you have to think about it as constraints. That's it. Consistency in the context of ACID is about constraints. What constraints? Column types. You cannot save a date in a varchar, like null constraints, length, foreign key, unique key constraints, or even custom constraints, like this one. If we add this constraint to our previous example, you will not get a negative balance, and the right transaction will fail. So you'll never withdraw more money than you had in the original account. Okay, and the third one, durability. To understand durability, you have to visualize how database systems work. And a database system, this is not just for relational databases. Any database systems work like that. So you have all your data is on disk in pages. You have for tables and indexes. However, accessing disk is very, very slow. So you want to minimize that and keep as much as possible in memory. So when you read something, you keep in the in-memory buffers. When you do the modification, you modify only the data in memory. You cannot, at commit time, it would be ideal if you can flush that, but that would be extremely slow. So the database, like PostgreSQL, only flushes the in-memory buffers every 5 minutes. So in between those 5 minutes, what happens if you just pull the cord from the server? You're going to lose all the in-memory data, right? So you need some additional mechanism to make sure that you don't lose your data. And that's how durability works. You have a log, the redo log. That's where you append what you have committed at every transaction. So if, for instance, the database is shut down, during recovery, it will apply all the log entries that after the last snapshot that was synchronized. So in the end, after recovery, you are not going to lose anything. So the redo log plays the role for durability. The undo log is for atomicity, to roll back, during rollback, to roll back to the previous state. However, this does not tell anything about concurrency, and that was the problem. It was not about atomicity, it was not about consistency, although we could have fixed it using a constraint, and it was not about durability. So there's something more. And of course you need a concurrency control mechanism, because you have multiple connections that work with the database. So ideally, everything, if everything is executed serially, which we saw that worked perfectly in that serial execution test, you don't have any concurrency issues. And in fact, there are some databases which work like that, which is VolDB. VolDB keeps everything in memory, and because it keeps everything in memory, it can allow everything to happen in a single thread. So if you don't have concurrency, you are not going to have any concurrency control problem. But that, for instance, that's how serial execution works. Everyone has complete exclusive access to the database. However, a database system does not work like that, because you have multiple database connections, and every database connection can do any read, any write, any modification they want. You need a way to control how those reads and writes are allowed to be interleaved, so that in the end you have a transaction schedule which is consistent, so which is equivalent to some serial execution. So you can allow a degree of concurrency, and as long as that's consistent and equal to some serial execution, you can say that that's correct. And let's see how that will happen. So in the same paper related to concurrency, Jim Gray said that the easiest method to use is to use locking. And this is exactly how what he describes here is exactly how two-phase locking works, where you have two types of lock. You have a read or a shared lock, and a write or an exclusive lock. Exclusive locks block any other lock access. Like if you write something, you cannot, and somebody else cannot write or cannot read that until you commit. Or if you have if you read something, others cannot write it, but they can still read it. So it's very simple to implement, and the only other requirement other than blocking between read and write is that you have to release the logs only after you commit or you roll back. So what does it give you? Not only that it gives you, when you use two-phase locking, what you gain is not only that you gain serializability, you get actually strict serializability, which means that it's also linearizable. Because this is how the consistency models look. On the left, you have the models which give you how you interleave read and writes and what anomalies you might get if you go below serializability. And on the other part, you have how operations are seen by other concurrent services. So for instance, linearizability tells you that everything happens, when you write something and you read it from a different connection, you actually get to read the same value that was written. For instance, if you don't have linearizability, which is called consistency in this TP theorem, that's what I said, that consistency means different things in different contexts. If you don't have linearizability, you can imagine a system like that, where you have a replication between a primary node and a follower, and there is an asynchronous replication. There's a lag between them. So now, when someone updates the account, it will take some time to replicate it. So the time flows from left to right. So a different client will try to read it, will see a value of 50 from a follower node, and they will think that it's okay to withdraw the money because that's what I read. And then a replication kicks in, and it will update the state. And then when we apply the change on the primary, we will see that we deducted more than when we're allowed. So that's how linearizability works. Because not everything is written and read atomically. Because if you had linearizability, after the first one wrote 10, when you read, you should have seen 10, not a different value. This one was eventual consistent. That's the term, eventual consistency, but it's actually more related to visibility. So when you have strict serializability, you have both of them. And when you have both of them, nothing bad really happens. The problem is when you go beyond that. However, this is not only strict to database systems. Actually, in Java, reads and writes are not linearizable. They are only linearizable if you're using volatile, because you have in the CPU you have multiple caches. And when you write something, it might be that you're only writing on or reading in your own cache. And if someone else modifies in a different thread, it might go in a different cache. So if you don't linearize everything in the main memory, reads and writes are not linearizable. So you still can have the same issues, not just in databases, also with Java. When you have concurrency, pretty much the same concurrency issue can happen if you don't allow concurrency control mechanism to provide a good, strong consistency model. However, even if two-phase locking was quite easy to implement and it provides a very strong consistency model, there is a problem. It uses too much locking. The more locking you use, you will see in Amdahl's law tells you that the more locking you use, the less you can scale, the less parallelism you can use. However, it does not show you the full picture, because if you take a look on the left, on where's the Amdahl's law, the one in red, you will see that you can go to infinite scalability, which is not true. And then in reality, the curve looks more like in the universal scalability law. It tells you that up to a point, you get parallelism, you can scale, and afterward, if you increase the number of connections or the number of threads in the JVM, actually the performance gets worse. And it makes sense. If you just start 10,000 threads in your JVM, it's not like your program is going to work faster. There's going to be so many context switches and coherency operations between CPU caches that will take the most amount of time, not the algorithm that you try to parallelize. So, two-phase locking worked. Back then, that was the context. They only had, the largest deployment had only 10,000 terminals and only 100 active transactions at any instant. Actually, a website nowadays can get way more traffic than that with any database you download. So the context has changed, so you cannot just use the same things that were developed back then. So even then, they realized that there are many other ways to address this serializability, because using locks, you can avoid conflicts, but you can allow conflicts. As long as you can discover them at the time of commit, you might deliver better performance in your application. And for instance, that's how MVCC was born. MVCC is not a new term. Actually, it's been in Oracle from 1984. It's been for a very long time. Other databases adopted it afterwards. But this one, MVCC, multi-version concurrency control, has been for some time, and it can provide some sort of serializability, although by default it does not. It provides a lower isolation level. But let's see how that works. In MVCC, you don't block. Readers and writers don't block anymore. So once you modify something, someone can still read the old value. And once you read something, someone can still modify it. However, this is just, words are not very easy to understand. It's much easier if you visualize it. So this is in PostgreSQL. In PostgreSQL, when you have a table, you have more columns than you see there. Actually, you have these two columns, xmin and xmax, which give you what transactions are allowed to see. When you are going to insert a record, you're going to see that the column xmin, which you can actually select. If you select all and xmin, you're going to see that value. So you'll see that in xmin is going to set the transaction ID of your current transaction, which tells how does it work. The other transaction, which have a higher transaction ID, after you commit, can see the record if they have a transaction ID, which is greater than the one who inserted it. Until you do the commit, only you can see your own changes, but other systems cannot see your change because you didn't commit. But afterwards, they can still see it because the second transaction, Bob, has a transaction ID which is higher than the one who created that tuple. Now, delete. If you have a record and you try to delete it, you will see that the record is still there. So actually in MVCC you're using soft deletes. You just mark the row that is eligible to be deleted. So you just set the X maximum, the maximum transaction that was allowed to see that record. Until you commit, if you delete it, until you commit, you can see that the row is deleted, but the other transaction will not see it. Will still see the old record because the old record is still there. Only after you commit, nobody will see the record anymore. But the record is still going to be there. So you need a garbage collector process to go and reclaim the old tuples. And that's exactly what the vacuum does in PostgreSQL. It works exactly like in Java. And now, using insert and update, that's exactly how insert and delete, that's exactly how update works. So when you do an update, you're actually doing a delete and an insert. So you have both tuples, both the old one and the new one. So when you are reading the updated from your own thread, you modify the record, you can see the modified value. The other ones until you commit, will see the old one, because that's exactly what multi-version concurrency control is. You have multiple versions in the same time, and everyone is directed to the version that they are allowed to see. So that's why, without using locking between read and write, you can still provide a concurrency control mechanism. And this one, of course, scales better, because otherwise, if I do a modification, the other one cannot read it until I commit. So that's pretty much how multi-version concurrency control works. And Atit basis has two ways of working, because it's based on what you are referring your snapshot to. If you are referring your snapshot to the time of when the query started, you can get a read-committed isolation level. Or if you put the snapshot and you can only view data as if it were at the beginning of the transaction, you get what snapshot isolation is. So basically you have only two isolation levels, which this one implements. And of course, even for locking and for MVCC, it's very bad in OLTP to have long running transactions, because you keep those versions for a very long time, and the garbage collector task is not going to be able to clean all that, and you are going to bloat indexes and your data. All right. So now there's a very interesting example to see the difference between two-phase locking and MVCC. Here we have a department, and now the sum is 90,000 in our department. And we have two users. One user wants to hire someone for 9,000, and the other user wants to give a raise for 10%, which is also 9,000. If we allow both of them to work in the same time, we will go over the budget, because our budget is 100,000. Under two-phase locking, you have Alice who reads the record, she takes the log, then Bob, when they try to insert, they do the read, and then when they try to insert, they cannot do the insert, because you already locked that those records, the employees. If Alice does not release the log, they will block and they will time out eventually. So Alice can proceed, and only one user apply the change. That's how two-phase locking works. In MVCC, that was avoidance. Here you have to detect it. So you read, Alice reads the salaries, then Bob comes. He can also read, because there's no blocking anymore. You can also do the read, and then you can even write. You can do the write of employees, because Alice did not block you to do so. However, at the time Alice comes back after your commit, and when she tries to update, Alice will get an exception, because the conflict was detected. The data is no longer the one that she read at the first time. So that's the difference between how things work in two-phase locking and MVCC. However, I'm giving you this example here, also in MVCC. You do the select, you read that you have 90,000 in your department, and then Bob comes, he hires directly, and then when you come and you do the update, both will work. Do you think this breaks serializability or not? Is this a bug or not? Or it's okay? It's a bug. It depends on what you think the bug is. From your perspective, your application logic, it might be broken, because if you take a look on the logs, you see that those were not, that should not have happened. However, from serializability, it's okay, because like I said, serializability means interleaving read and write so that they are equivalent to a serial execution. Here, a serial execution would be if the insert happened afterwards. You'd gain the same outcome. So here, from the definition, it's serializable. However, it's not linearizable, because only two-phase locking was linearizable. Serializability does not tell you that you have to have a fixed flow in time. The time should follow the exact wall clock time. So that's why it can allow to reorder operation from this perspective. So this is correct. You can still use serializability and still have bugs in your application if you still based on how time flows. So yeah, that's important to keep in mind. The next thing is, in the standard, you see that in the beginning, when SQL appeared, everything, it was meant to be serializable. So they didn't talk about any anomalies, because once you use strict serializability, you don't have any anomalies. However, they realized that does not play very well with performance. So then in SQL 92, they decide that you can relax the isolation level, but then you can have some problems. And the standard only tells you about 3 issues: dirty read, non-repeatable read, and phantom read. But in reality, you have more of them. You have read skew, write skew, and you also have dirty write and lost update. Dirty write is not very worth talking about because dirty write, if a database has dirty write, it cannot even provide atomicity. Now, dirty read is quite simple. If you read something and someone comes in and modifies that record, and you can read the uncommitted value. Now, if everyone commits, there's not going to be a problem. It's a problem when the other one rollbacks. And now you are reading, Bob has read a value which no longer is found in the transaction log. So you take a decision on something that is not trackable. Actually, it didn't exist because it was rolled back. Actually, this can be, most of the time, this can be a problem. But there is a use case when actually using this is actually okay. You know why? What use case? That actually might be a feature, not a bug. We're not tracking a progress. Some transaction does some work, and then you come with a transaction that allows dirty read, so you can read its progress before the commit, so you can display a progress bar. So actually, it depends on the situation. Sometimes you can even benefit for having these anomalies. Non-repeatable read is you read a value, you read the first value from the database, someone comes in, modifies and commits it, and when you read it again, the value has changed. So the reads are not consistent. Between the two, between your reads, someone came and modified it. But then in between, you might have taken a decision there. So that's why this can be an anomaly. Phantom read is actually the same, but it applies not just to a tuple, to a range. So you have a range, like we had there, a range of employees, a range of comments, and someone comes in and adds a new comment, and when you read, you pick that up. So the standard only tells you that you can have these issues, but in reality you can have more. For instance, you can have read skew. Here you have two records which must be always updated in sync. So you have the post, which has a title, and then the post detail must mark who made that modification. So here in between your reads, you're reading the first post, someone comes in, modifies both of them and commits, and by the time you read the post details, you get a combination of records that never existed, because it's neither the first one nor the second. It's a combination of them two. That's how read skew can happen. And you also have write skew, when you read both these two records, and now Bob tries to modify both the post and the post details, but the post details, because it has the same updated column, it's not updated, because probably you're using JPA or Hibernate, and which is exactly how it works, because of the dirty checking mechanism. And then Alice does the same. She tries to modify the post and the post details. However, the post is exactly the same, like she sent the request to, and she only updates the post details. So she will, Bob updates one record, and Alice updates the other ones, although both have read previously the other version. So in the end, you get to a combination of records that also did not exist. So it's a skew between them. And also you can have lost update. Here you read a record, and in a different transaction you come and you modify it, and then when you do an update, it's based on the previous value that you read, but not the one that is now in the database. So you're going to lose that update. It's exactly what we saw when we were withdrawing from an account, and the value is not the one that we read, it's a different value. So you can also have this. However, in the SQL standard, they tell you that the isolation level can control how many anomalies you can get, and theory looks something like that. So under serializability you get nothing, and then the more you go to a weaker isolation level, you can get one of these. But in reality, it looks way different than this. This is how it looks in reality. For instance, this is Oracle, where in read committed it's the same like the standard. But then what they call serializable in Oracle, it's not serializable. It's actually snapshot isolation. And in snapshot isolation, you cannot prevent write skews. So you still have, that's not a serializable outcome that you'd get on Oracle. On SQL Server, by default, they still use two-phase locking. So when you take a look on serializable, they prevent everything, because that's how two-phase locking works. And only if you want, you get MVCC. So you get read committed under MVCC or snapshot isolation, which is named properly, because that's what it is. It's not serializable. In PostgreSQL, repeatable read is snapshot isolation, but then they provided an improvement, which is called a serializable snapshot isolation implementation, which allows them to provide serializability at the cost of some false positive that might appear. But actually, this is correct. This is actually what you will get is a serializable outcome. And in MySQL, by default, you have repeatable read. On the other databases, by default, you have read committed, which is interesting because you have a lot of anomalies that can happen. So you always have to think about it. The default sometimes might provide many more vulnerabilities than you think of. So here, by default, you're on repeatable reads. So you can even have lost update, not just write skew. And serializable in MySQL works by taking logs in InnoDB. They just take logs on data that you read under serializable, or even across ranges. However, that's not all, because when they designed it, that was the era. It was the time of mainframes, exactly like in that paper, where you had terminals and you had a mainframe and you had complete access to the database. During your transaction, you kept your transaction open for 2 minutes, you did all the writes on your read, everything happened in a single transaction. But that's not how we use databases anymore, because nowadays we use, on the internet, you cannot just use a single transaction for your reads and your writes. You do the reads in one transaction, you display them to the user, and when you come back, it's a different transaction. It's a different HTTP request. So if you think about it, ACID no longer helps you if reads and writes operation are split among different transactions. So because you have an application level transaction that spawns over multiple database transactions, you also need some application level concurrency control. Because if you don't have it, it will happen something like here. For instance, you read a product with a quantity of 5 and you display it to the user, and then a batch process comes, updates the quantity from the warehouse. Now the quantity is 0. And when you come back, you select to decrease it, and it's going to be -1 because it's no longer 1 that you read. It's no longer 5. So here, even in serializable will work like that. So what can you do? The first thing that you can do is to keep up the version that you had. So let's have a consistent read, to use the same read. So you read, you keep it in the HTTP session, then the other process comes, modifies the quantity, and then if you modify, you decrease it, because that's exactly the operation that you did in your browser, just decrease the quantity, and you update it, you are still going to have a lost update. So how can we fix it? To fix it, we can use optimistic locking for that. We can use a version column, and then the update and deletes are going to take the version into consideration as well. So by default in Hibernate, when you update or delete something, you expect to have an update count, because in the JDBC execute update returns an integer, and that integer. And the integer can be, you expect it to be 1, because you expect the record to be here. It can be 0 only if the record does not exist, or if the version has changed. And that's how you can serialize conflicts. So if you're using optimistic locking, you read the product, the quantity is 5, and then the update comes from the batch process, they update the quantity, the version is increased from 1 to 2, and now when you try to apply your change, it will fail, because the version is no longer 1, and your update references the version, expects the version to be 1. So you get a 0 update count, and it will not work. However, that's not all, because you can also have this situation here. If you're updating different columns, if you're reading from 3 users and one updates the title, the other ones cannot make any progress, because, and even if they modify different different properties there, those properties might not overlap. So here we get this exception, and the obvious, what people will do is just remove the version column, because what can you do about it? However, you can still fix it. You can just split in many one-to-one relations based on subsets which should be treated independently. If you do that, then everyone updates its own subset. So then you have multiple versions because you have multiple rows. And even if you extract everything using joins, it's not going to be slow, because you can always have a single result. So you don't fan out. But you can also use this in Hibernate, which is called dynamic update and optimistic lock type dirty, where you remove the version column, and then when you update, you don't use the previous value of the type of the property to make sure that it has not changed. So using this, you can still bypass false positive in optimistic locking. So now everyone can modify the post titles, because these are not overlapping anymore. And also, JPA offers even more than that. There are even explicit optimistic locking modes which you can use, like this one, optimistic force increment. And here you have a repository, like in Subversion, which can apply commits. And if you remember Subversion, every commit increased the repository version. You cannot just update the version using set version. You have to use something else. And that's how you use optimistic force increment. When you read the repository, you read it in optimistic force increment mode. And then when you do the insert, by the time the transaction commits, before it commits, it also updates the repository. So the first transaction comes, applies the commit, changes the repository version, and when the second transaction tries to do the same, it will fail, because now the repository version has changed, and you need to do an update to fetch the latest state and do the conflict resolutions. So basically this is how we starting from stick serializability, we got to snapshot isolation. Then we also have the time when in NoSQL where you didn't have neither linearizability nor you had serializability. And nowadays the trend is to have those again. If you think about databases like VolDB or Spanner, the new databases actually provide serializability. Like for instance MongoDB 4. They provide now ACID for multiple documents. Not just even Google for Spanner. This is from the Spanner paper. They realized that actually for them, it's better, for Google developers, it's better to use transaction and tackle the problem of overusing transaction instead of not having them and risking to have issues. And with that, we're pretty much over this. And now if you have questions, we have, I think we have plenty of time to address them. Oh, no question? Otherwise, you can find me in the hallway. I'm going to be here today and tomorrow as well. So if you have any questions about, not just about this, about Hibernate as well, just meet me in the hallways and ask me anything. So thank you for coming. And